In this video, we're going to go ahead and cover section 9.6, Counting Principles, part of Unit 9, still Sequences, Series, and Probability. This is kind of a fun chapter for those of you who like puzzles and any kind of solving of that sort. We're going to start right away with the fundamental counting principle. So this principle says that if we have two events, and of course you can extend this to more events and events, the first event can occur in this many ways. We're going to call that M sub 1. After the first event happens, well, then the second event can occur in M sub 2 different ways. The number of ways the two events can occur is M1 times M2. So, for example, let's say we're picking a number from 1 through 5, and you're trying to figure out what are the odds of getting a 1 out of those 5. So that'd be like 1 out of 5. That'd be your first event, E1. Um, Now let's say we're going to go ahead and do it again and say, well, now I want to get a 2. What are the chances of getting a 2? If we leave the 1 in there, then your chances are still going to be 1 out of 5. So you have 1/5 times 1/5, just multiply it, and that's basically what this is. That would be considered using this principle um, without replacement. So you're not, I'm sorry, with replacement, where you basically put everything back in. Now without replacement is saying you would take out the numbers. So let's say we want to get that 1 out of 5, so we get the 1. Now we remove the 1, and now to get a 2 is going to be 2 out of 4, or 1/2, because you removed one of the possibilities that we had. Okay, so those are just two different things you might think about. And of course, like I mentioned, it can be extended to three or more events, where you basically just multiply to whatever, last event you have. Let's go ahead and look at example number one. We have a combination lock. Okay, so combination lock will open when you select the right choice of three numbers. So 1 to 30 inclusive, meaning we can choose 1 and 30 as well. How many different lock combinations are possible? Okay, so we have, out of the 30 numbers, okay, we have to do we need three of them to work. So let's kind of define what the events would be. So you can kind of see the second problem. That's okay. So we have for event one, okay, well, out of all for event one, we have 30 possibilities, right? 1 to 30 is 30 numbers. So we have 30 different ways we can get that. So it's kind of like this would be kind of like our M1. Okay. For event two, so now we're picking the second number. Well, we're not taking any of these numbers out. So this is with replacement, which means we also have 30 possibilities. Okay. For event three, well, again, we're not taking any numbers out. This is with replacement. We're putting all numbers back in there. So we still have 30 possibilities, which would be M3. So based on this, we would have 30 times 30 times 30, which if we multiply 3 times 3 times 3 is 27, three zeros. So that means there are 27,000 possible lock combinations, which is kind of a lot. So if this was some kind of actual puzzle, it would take the person quite a bit of time to figure out the lock combination. Okay, so there you go. There's the first one. Second example, we have a product's catalog number is made up of one letter from the English alphabet, followed by a five-digit number. How many different catalog numbers are possible? Again, there's no mention of once you get something, you can't use, the remaining numbers or whatever. So this is also going to be with replacement. So let's see. For our first event, event one, we're trying to figure out a letter from the English alphabet. So the English alphabet has 26 letters. So that means it's going to be 26. So this is our M1. And by the way, event one is basically I'm going to say the letter. That's what event one is. Okay. Event two would be, well, we need to do, let me see. One letter for involved. Oh, five-digit numbers. So it's a five. So event two is going to be one of the five-digit numbers. So we'll say, I don't want to say number one. We'll say the first number. So the first number is event two. Now you got to be a little careful here. So five-digit number, you're basically thinking from 0 through 9, because those are the digits that we have for numbers, 0 through 9, 0, 1, 2, 3, 4, 5, 7, 9. So from 0 to 9, the possibilities are 10 options, because 0 counts as a possibility. So in other words, if you count those numbers, here, I guess I can put that here, from 0 through 9, that's 10 numbers. Okay, so that means that 10 is going to be our our second amount of possibilities, okay? For event 3, we're trying to find the second number now. Remember, there's 5 numbers. Well, we have the same, again, we're not omitting any of those numbers, so we still have 10 options. So 10 is our M3, and maybe you can kind of see what's going to happen next. For the fourth event, this is our third number. We also have 10 options, so that's M4. For the fourth number, and I'm almost out of space here, which would be the fifth event, we also have 10 options, so M5, and it's really getting close to the bottom here. For the fifth number, we have event 6. So this one actually has 6 events, which would be M6. Because of that letter, we have the option with the letters, and then we have all this. So altogether, we're looking at 26 times 10 times 10 times 10 times 10 times 10. So 26 times 10 times 10, there's 5 of them. 3, 4, 5. If you multiply this out, we get a really big number. Let's see, 26, and then 1, 2, 3, 5 zeros. So 1, 2, 3, 4, 5, which is 2,600,000 possibilities. So possible ways, I guess I can say. And that's it. That's it for this first concept of the fundamental counting principle. Okay, let's go ahead and look at some more combination permutation type of stuff here. Actually, we're going to look at permutations first. So what is a permutation? A permutation is basically when you take um, a certain number of elements and you order them in a certain way, such as first, second, and third. So for permutations, and I did put this here, order definitely matters. So it's when order matters, we call it a permutation. Let's look at example number 3. Let me kind of get this to, there we go. It says how many permutations of the letters W, X, Y, and Z are possible? Okay, so in this one, we want to make sure that each since it's in how many different permutations, that means that the order does matter. So we can go this way, we can put the X first and W, and that would count as another option. So again, order does matter. So for my first, I guess you could say spot. So let's see, we have 5 letters, 1, 2, 3, 4, 5. So for this first position, we have about 1, 2, 3, 4. Oh, I'm sorry, it's four numbers. What am I saying? 5. It's only 4. I'm sorry, ignore that. So there's 4 options, which means we have for the first spot 4 options. Okay. Now, whatever this letter comes out to, it's taken out of the mix. So let's say if it was a W. So now that we have W in the first spot, what we're left with for the second spot, 1, 2, 3, 3 possibilities. Okay, and now that one's gone. So this would be an example of without replacement. In other words, once you use up one of the elements, you can't use it anymore. Okay. For the third position, we're left with two left, so 2 options, so 2. And then, of course, the last one's going to be the 1 option. So what does that mean? Well, that means that we have 4 times 3 times 2 times 1, which is the same as 4 factorial. Yeah. In this case, if we multiply this, we get 24 possible permutations. So 24 possible permutations. And you could actually list these. You could, try them all out. That's probably the first method. Anybody who's not familiar with this would do. They would say, well, let me try all the different combinations. And they would get 24 possibilities, which is fine. You can do that. But what happens if you have like 10 letters? You don't want to try to list all that. That's going to be a lot. It's going to be 10 factorial, which is a pretty big number. So thank goodness for some formulas. Okay. And with that said, here is the actual definition of the number of permutations of n elements. So as you can see, it's basically the number of elements times the next one and the next one all the way till we get to 1, which is the definition of a factorial, which we have seen before. So this means that there are n factorial different ways of ordering n elements. Okay, so let's try another example. We have a Harry Potter United Club has 5 members. In how many different ways can there be a president and a vice president? So this one's a little bit different because we only want 2 spots, right? So here's how one way to think about it. We have the option for the president, and then we have the option for the VP, the vice president. So what do we have? Well, if we have the president and there's 5 members, that means that there are 5 options for the president. It can be, one of those 5 people. Um, After we've chosen the president, well, we have the position for the vice president. So the vice president, since we already have one person who took over the presidency, there are only 4 options left, which means in this case, we only have 5 times 4, which is 20 possible ways. So I'm just gonna put 20 ways. So how is this one different from the one before? Well, let's take a look at the official definition. This one's different because in this one, we're taking permutations of n elements r at a time. So we only want a select number from the total. We don't want them all to be in order. We just want a few of them. So this one goes as follows. The number of permutations of n elements taken r at a time is this, where we have our total divided by n minus r factorial. So if you kind of think about the one we did down here, we could have used this formula to get the same answer, okay? And we've kind of seen a rendition of this in the past, so it shouldn't be too difficult. I have an example that kind of goes with this. And I did solve this one because of the time. So example number 5 says we have 8 horses that are running in a race. And how many different ways can these horses come in first, second, and third, assuming there's no ties? So here's the solution. We have a total of 8 elements, right? There's 8 horses taken 3 at a time because we only want first, second, and third. The rest of them, sorry, we don't need them. So that means that n is equal to 8 and r is equal to 3. Um, so it looks like the following. We plug it into our formula, P83, so 8 factorial over 8 minus 3 factorial, which we know how to work. 8 minus 3 is 5. Expand this, 8, 7, 6, 5. The 5 factorials are gone, which means we just have 8 times 7 times 6, which is 336 ways, which kind of leads back to the one we did before, where you can basically just multiply the number that we had from the beginning that many spaces, if that makes any sense. If that doesn't make sense to you, use the formula. The formula will not fail you. Okay. Let's look at another way we can do permutations. We have distinguishable permutations. Okay, so in this case, we want to consider a set of n objects where we have n of one kind, n two of the second kind, and so forth. Basically, where n is equal to all the different types that we have. So the number of distinguishable permutations of these objects is given by the following: n factorial divided by each of those events or each of those possibilities factorial multiplied by each other, so the product of all those factorials. Let's go ahead and look at an example of this one. This, like I said, this video is not too bad. It's just maybe a lot of copying because of the word problems. It says, in how many distinguishable ways can the letters in mitosis be written? Ooh, look at that, biology. Not my favorite subject, but let's see. So for my n is going to be basically the total number of letters. We have 1, 2, 3, 4, 5, 6, 7. So 7, okay? N of 1 is going to be well, one of these, right? One of these letters. So I have M. We can say M is going to be one of our events. And M only happens one time. So 1. N2, what's after? Let's see, I, the letter I. We can do that. That way we can kind of match them up. So I is in here twice. I'm going to circle as we go. So we have N2 is going to be 2 times. This event happens twice. We have 2 I's in there. The letter T is next, so that would be N3. And that one is only, let's cross those out, that's only 1 time, so 1. Then we have the letter O, that would be N4. And the letter O only happens 1 time also. We have the letter S, which would be N sub 5. And that one happens 2 times. So these are going to be all our different n factorials. So let's go ahead and apply this all to the formula. We have 7 factorial over, so remember n factorial goes on top, over 1 factorial times 2 factorial times 1 factorial times 1 factorial, make sure those look like factorials, times 2 factorial, which is a little bit, tedious because we don't really have to write the ones. 1 times anything is 1. So I'm going to rewrite this just to make it look, a little nicer. 7 factorial over I'm going to put both of my 2's, 2 factorial, 2 factorial, because the 1s are just, 1 times whatever is the same thing. So this is what I have to work with. I'm going to go ahead and reduce that. So 7 times 6 times 5 times 4 times 3 times 2 factorial over 2 factorial, 2 factorial, which gets rid of one of them. Okay, so I'm left with 7 times 6 times 5 times 4 times 3 all over 2 factorial. Remember, 2 is just, it's going to be 2 times 1, so it's just 2. And from here, I can probably simplify it. I'm going to get rid of the 6 just because it's a bigger number. So 6 divided by 2 is 3. So this is what I have to work with. 7 times 3 times 5 times 4 times 3. So let's see. I can do, I like to do mental math. So 5 times 4 is 20. 20 times 3 is going to be 60. So I have 7 times 3 times 60, which is 21 times 20, right? I'm sorry, 21 times 60. What am I saying? 7 times 3 is 21. Okay. And if I multiply this, I get 6 times 2 is 12, 1, 0. So I believe it should be 121. I think I'm missing a 0 somewhere. Let me double check this real quick because, mental math doesn't always work. So let's see. 7, 3, and then 5, 4, 3. Yeah, I forgot a 0 somewhere. Oh, no wonder. You see what happens? 6 times 1 is 6, and then I forgot the 0. So there we go. 1260. Now I'm adding the 0. Okay, ignore my mental math, but you get it. 21 times 60 is 1260. 6 times 1 is 6. 6 times 2 is 12. Put the 0. And there you go. Mental math is not required, by the way. Like I said, your teacher just likes to do that. So there you go. There is the answer for this one. There are 1,260 ways that we can write distinguishable ways we can do these letters in. Let's look at the last example here. We do have one more definition that goes with it. Combinations, when order does not matter. So permutations, the order does matter because we want to make sure we have it a specific way or we have only certain elements out of the total. This one, order doesn't matter. So a great example is kind of like a combination lock. Yeah. Let's look at the definition. We have the number of combinations of n elements taken r at a time is given by the following: n factorial over n minus r factorial times r factorial, also equivalent to basically the permutation divided by r factorial. So kind of like this part without the r, that's a permutation. With the r, it's a combination. So pretty cool. I like to think of it as n choose r. So you have n elements, you're only choosing this many elements out of that combination. So let's look at one more example, and that'll be it for this super cool set of notes. Example 7. In three-card poker, a hand consists of 3 cards dealt from a deck of 52. How many different three-card poker hands are possible? And again, order is not important. So for this one, it looks like our n, which is the total number of elements, is 52. So we're choosing out of 52 cards. That's what n is. And out of those 52 cards, we are choosing 3 cards. So 3 cards. So r is equal to 3. So all we have to do is plug it in. So if you want to think of it as our notation, we have 52, choose 3. Oh, I forgot to write this on the other page, but another way to write this is like this: 52, choose 3. I kind of like to see it like that. But anyway, that's for later on, college. We will do 52 on the top, and then 52 minus 3 on the bottom because it's n minus r times r, so 3 factorial. And we just reduce this, so it looks like we're going to have 52 factorial over 52 minus 3 is 49 factorial, and we still have the 3 factorial here. I'm going to expand this a little bit. 52 times 51 times 50 times 49 factorial. I'm going to stop there because I have a 49 factorial on the bottom. I'm going to leave my 3 there for now. So this is gone, and I'm going to rewrite it maybe not one more time, maybe 2 more times. 52 times 51 times 50 over 3 factorial is 3 times 2 times 1. So I can see I can reduce this one by 3, which is 17, this one by 2, which is 25. So I have 52 times 17 times 25. which I'm not gonna attempt in my head right now because we don't wanna embarrass ourselves here. So go ahead and multiply that out. We get 52. Let me see, 17 multiply 25. I am getting 22100. And just for anyone that's listening, I probably could do it in my head, but it's a Friday. So there's the answer. We have 22,100 possible ways that this is possible. And that is it, guys. That is it for this video. So hopefully you understood. If you have any questions, as always, please reach out and let me know.